Oh, hello. This is session 2 of the 590. Today we're going to be talking about portfolio theory and some ideas for multi-criteria optimization. Now, in selecting a portfolio of stocks or assets, sometimes they don't have to be all risky assets. They could be assets that have a risk-free, like treasury notes or treasury bonds. But what we want to do is we want to maximize the portfolio's expected rate of return, R bar P, and minimize the portfolio risk, sigma P. Sigma P is just the standard deviation of the portfolio rate of return. Okay, so now, because of this, let's do 1, 2. We have a multi, which is 2 criteria optimization problem. Remember, before we said that if we just had if we could estimate the portfolio expected rate of return and we weren't worried about risk, then it would be a simple linear programming problem. But now, when we have to consider risk here because stocks are inherently risky. Now, multi-criteria problems when we say in multi-criteria problems, defining optimal solutions is not as straightforward as in single objective optimization. Okay, so why don't we say, why is this? Okay. In single objective optimization, the optimal solution, actually you could have more than one solution, is the one with the best objective function value. So if we're maximizing, the best objective function value would be the highest objective function value. This is easy to define. Since with one objective, the objective function values we're getting a little low there. Let's go to the next page. Can be totally ordered. Okay, so what do we mean by totally ordered? Suppose there are two objective function values. And we are maximizing. Okay. And let these two objective function values be z and z hat, or what's called z star. Okay, so we have these two objective function values. Now, we can totally order these because we can put, say, z here and z star here. So each of these takes one and only one place on a line. One and only one place on a line of objective function values. So whereas you may have a number of optimal solutions, you only have one optimal objective function value. Now, another way to put this is that the objective function values can be ordered. Like we said, totally ordered. Okay, let's say that we have the following. In other words, they obey the trichotomy law of, we'll say, real numbers, but we don't have to worry about real numbers. That is, for any two numbers, one and only one, two numbers, and let's call these numbers A and B, one and only one of the following three things can occur. We'll say either 1, A is greater than B, or 2, A is less than B, or 3, A equals B. Okay. Now, the problem is that in multi-criteria optimization, this is not the case. This does not hold. We can't guarantee that this holds here. In other words, vectors, in our case, pairs, where our pairs will be the following, will be risk and expected rate of return, cannot be totally ordered. They can only be what we call partially ordered. And we'll give some examples. Don't worry about some of this mathematics. We'll give some examples to make this clear in portfolio theory case. Okay, let's take an example. Let's suppose that we have three portfolios. To choose among. And we'll call these X1, X2, and X3. Okay. Now these, and further suppose that their output pairs are as follows. Okay. And the output pairs are going to be what? They're going to be sigma r bar. Sigma p r bar p. Okay. So let's assume that they're as follows. And we'll say that first we have 1, 1. Then we have 2, 1. And then we have 2, 2. Okay. So this is sigma 1. This is r bar 1 for the first guy. This is sigma 2. This is r bar 2. This guy is sigma 3. And here we have r bar 3. Okay? Now, let's see if we can find the optimal portfolios. Amongst these three. Okay. Now, clearly, X2 cannot be optimal. Why? Its output pair is dominated by both X1s and X3s output pairs. Okay, let's see that. Because X2's output pair which is 2, 1, has a higher level of risk equals 2 than that of X1, whose level of risk we have that sigma 1 equals 1 for the same expected rate of return. And the expected rate of return is 1. So this one has more risk for the same level of expected return. Therefore, it's clearly dominated by 1, 1. It's also dominated by X3, since its expected rate of return equals 1 is less than X3's for the same level 2 of risk. Okay, so we can eliminate, so X2 can be eliminated. And the optimal solutions to this problem and the optimal portfolios are X1 and X3. Whose output pairs are 1, 1 and 2, 2. Okay. So the set, so now we have a set of optimal solutions. And more importantly, a set of optimal outcome pairs. Because in single objective optimization, we could have a set of optimal solutions, but each of them would have the same objective function values. So this is the more critical thing. Okay. And these outcome pairs do not satisfy the trichotomy law since, let's look, we have the 1, 1 and 2, 2. Since 1, 1, 1 is not greater than 2, 2, it's not clearly better than 2, 2. 1, 1 is not less than 2, 2. Remember here, we're minimizing one and maximizing the other. And 3, 1, 1 is clearly not equal to 2, 2. 1, 1 has a lower level of risk than 2, 2, but it also has a lower expected rate of return. Likewise, the same thing if we want to look at less than, and clearly 1, 1 is not equal to 2, 2. So it's a little trickier here. Now, let's look at, let's skip right to the chase here. Let's look at a graphical representation of the portfolio problem. And this is the way we're going to do it. On the vertical axis, we're going to look at the portfolio expected rate of return. Now, we could also just have, instead of having a portfolio rate of return, this could be just the expected rate of return of some stock or asset. Likewise, on this one, we're going to look at the risk as measured by the standard deviation here. Now, here's what we typically have. We typically have kind of an arrow-shaped thing here. We'll see this in the book. Okay. Now, what do we want to do? We want to maximize our expected rate of return, and we want to minimize our risk. Okay. So let's look at a point on here. Let's take a point. Let's take a point on here, and we'll come across, we'll call this R bar hat P, and we'll come down here. That's not a very straight line, but bear with me, and we'll call this sigma hat P. Okay. Now what happens here? Let's extend this line up and extend this line this way. Now what do we see about this point here? And let me write it on the next page. We'll see that 10, and let me do something else here before I do that. Good. Let's draw a set X. This is the set of feasible portfolios. And we'll put a little guy here, and we'll call him XP. And this XP map output is that point there. We'll call that XP hat. Okay? And we'll call this set of feasible output pairs Y. Okay. Now let's talk about what do we have here. Now we'll say that X hat P is optimal Alternatively, we call this efficient. When we say is an optimal, efficient, or Pareto optimal, sometimes called a non-dominated. I'm going overboard here. Let's go here. Non-dominated. Solution. And we'll say why. Okay, let's look at this. For any value of RP, R bar P, and we'll say R bar P hat, it minimizes risk. So for any value of expected rate of return, it minimizes risk. Let's draw that here. R bar sigma. Okay. So we take expected rate of return, say it's here, R bar hat, and we go along, and this point here minimizes our risk, right? Because our risk is on the horizontal. Along here, all these other guys have higher risk. than our point there. Likewise, for any level of risk, say sigma hat P, it maximizes the expected rate of return. So let's see if we can draw another little picture here. It'll be small. And we'll go like this again. And we'll see that we'll take a level of risk here. Sigma hat. And we'll see here that this maximizes our expected rate of return over y. We should say that. And this should be over y too. Y is the set of feasible output pairs. Okay. So what do we have? So the set of optimal solutions in outcome space equals what we call the efficient frontier is as follows. Okay, let's look at this again. Let's draw it. Here's our RP, R bar P. Here's our sigma P. If we draw this, oh boy, that should be smoother. So the set of an outcome space is this set here. All the guys on there are efficient. Remember, this is Y, and this is some X set of feasible portfolios. Okay. All of those guys have this property that for any level of expected rate of return, they minimize risk. And for any level of risk, they maximize the expected return. Let's write that out. For any level of expected rate of return, R bar, they minimize risk. And for any level of risk, they maximize the rate, the expected rate of return So they're along the efficient frontier. Now, let's look at this efficient frontier. Let's look at this again, and we'll see something interesting. Okay, let's draw the efficient frontier here. Let's draw it in red. Okay, and we'll put the set X here. And this is the set Y here. Now notice what? Notice that the efficient frontier is, and we'll call it concave. Don't worry about concave right now, but it's increasing. Okay, and this increasing is the important thing. That efficient frontier is increasing. And why does that make sense? This makes sense because rational investors would only take more risk if they would get a higher expected rate of return. Okay. So it only makes sense that the only reason that you would bear more risk is that so that you would get a chance to get a higher expected rate of return. Okay. So this is critical. Now, what else do we have here? Now, let's look at an easy way, graphical way, to find out if a portfolio or stock is efficient or not. Well, we can just have a stock is efficient. Okay. Let's draw our situation again. We have a sigma p, r bar p. Okay. Okay, good. Now, let's take a point, say this point here. We'll call this R bar P hat. And we'll call this guy sigma P hat. Okay, now, let's draw this here. Let's go below. So anything below here has, when we're going down, what do we have? We get lesser values of the expected rate of return, or lower values. And if we go this way, this gives us what? This gives us higher levels of risk. So let's call this the following. Let's go like this. And we're going to call this guy here. We're going to call this lambda hat equals so-called domination cone So what does that equal? That equals sigma hat P R bar hat P plus all the outcome pairs that sigma hat P R bar hat P dominate. So anything in this area and Y is clearly dominated by that. Now, let's go the other way. Suppose we have higher expected rate of returns and less risk. So then we're going to get this thing here, and this we're going to call hat, and we're going to put a star there. That's a direction of increase. We're going to say that this is the polar, and we'll define what we mean by a cone, equals that sigma hat P R bar hat P plus all the outcome pairs that dominate our point, sigma P hat, R bar P hat. I apologize for how small I wrote that. We're trying to get in there. Okay, now let's define these points here. First, let's define a cone. We'll say a definition. We'll say a cone pointed at the origin, in other words, pointed at 0, has the following property. And we'll call this cone, let's just call this cone S. has the following property. If y belongs to S, then lambda y also belongs to S for all lambda greater than or equal to 0. Okay. So that sounds like so much gobbledygook, but it's very easy to see graphically. Let's look at graphically. Here's a cone, and let's shade it in. This goes on forever. And so if we have a point here, y, in that, then the straight line through y, or the ray through y, is also in the cone. So for any point in the cone, the straight line through it is always in that cone for all lambda greater than 0, greater than or equal to 0. Okay, now this cone, this general cone here that's pointed at 0 would be a great cone to get if you were getting ice cream, because it goes on and on and on forever. So unfortunately, ice cream cones stop off, so you can't get everything. Now, having said that, we can say that. Now, how do we use this concept to tell if a point is efficient? We'll say that 16, and let's say a portfolio is efficient if and only if its outcome pair and what we call this x hat, and its outcome pair sigma hat r bar hat is the only outcome pair both in lambda star hat and y, the set of all outcome pairs. In other words, that's exactly what's going on here. If we look at this, here's our efficient frontier. We have r bar hat, sigma hat, or just sigma, and here's our set of y, our outcomes. And if you take any guy along this efficient frontier and then you draw the polar cone, and that polar cone, that's the only guy that's both in y and in that polar cone. It's the only guy that's in y in that polar cone. So this guy here, if we look at this guy, let's draw an x. Okay. Okay, and we'll draw this as a lambda hat star, and this is r hat p and sigma hat p. So there is our lambda star. Now let's look at another point. So let's say that this guy went from here to here. Now let's take another point. Let's take a point here, and suppose it goes to here. Now look at this point. That point's in Y, but what happens? That is in Y, intersect the domination cone. So this is, the blue part is the domination cone. There. So what does this imply? That let's call this guy X squiggle, okay? Implies that X squiggle is not efficient since we have its outcome pair is in lambda star intersect Y. So it's both in Y and in lambda star. Okay? So graphically, it's always easy to see which points are efficient and which points are not. Remember, when you're going up, we have lower risk, higher expected rate of return. So you can think of this part as a direction of increase. In fact, it's a vector analogy of the gradient, where the gradient typically shows the direction of maximum increase. Here we have this cone showing the direction of increase. There. Okay, I think that's probably enough for today. We'll go on some more about portfolio theory coming up, and we'll get to a lot of interesting things. One of the things that we'll show is that one of the most important things about portfolio theory is that you should diversify your stocks or different assets, or in fact diversify across portfolios. Yeah. And we can even prove that mathematically. So that's a nice result. Okay, well, thank you very much. I look forward to seeing you tomorrow.